So shall I share my screen?
No, we'll tell you to share. You have already tested. You can test it if it is.
Yes, yes.
You can test it. Huh? Already it is tested, so it will work. No issue at all. So, a hearty welcome to all the participants of this lecture series 54, distinguished lecture series 54. This lecture series is being jointly organized by INAE Bhubaneswar chapter, IIT Bhubaneswar, IMMT Bhubaneswar, NISER Bhubaneswar, IEEE Bhubaneswar section, and Sikha Anusandhan University. We are actually hosting here. So today's lecture is by Professor Susmita Surkole. She is a visiting professor now in Department of Computer Science, Ashoka University. Her talk is going to be on design automation for quantum computing systems. The details, of course, she will tell, and gist is circulated to you. Now, so far as Professor Susmita Surkole is concerned, she received her BTech honors degree in electronics and electrical communication engineering from IIT Kharagpur, and PhD degree in computer science and engineering from Jadavpur University. She has been a faculty member in the Advanced Computing and Microelectronics unit of the Indian Statistical Institute, Calcutta, since 1999 and retired as professor in 1924. She is now a visiting professor of computer science at Ashoka University. During the period 1993 to 1999, she was the reader in the Department of Computer Science and Engineering of Jadavpur University. Prior to that, she was a postdoctoral fellow at the University of Nebraska, Lincoln, and a research assistant in the Laboratory for Computer Science in Massachusetts Institute of Technology. She was also on a sabbatical at Princeton University and Intel Corporation, USA. She is presently a KIT International Fellow, Excellence Fellow. Her research contributions are in the area of algorithms, design, automation for VLSI, physical design, fault modeling and testing, synthesis of quantum computers, and graph algorithms. She has co-authored several technical papers in leading international journals and referred conference proceedings, a chapter in the handbook on algorithms for VLSI physical design automation, and co-edited 3 books. She was the general co-chair of the 29th International Conference on VLSI Design, 2016, and technical program co-chair of this 18th International Conference on VLSI Design, 2005, and 11th Symposium on VLSI Design and Test in 2007, and IS VLSI 2011, and has served on the program committee of several international conferences. She was on the editorial board of the IIT Computers and Digital Techniques and IEEE Transaction on VLSI Systems. She was a distinguished visitor of IEEE Computer Society of India and a fellow of Indian National Science Academy and an Indian National Academy of Engineering. She recently became the INSA Fellow. Congratulations to her. Now, she is senior member of IEEE, member of Associate for Computing Machineries, IIT, VLSI Society of India, among other awards. She was the recipient of President of India Gold Medal from IIT Kharagpur. And that is really very, very coveted award that she has got. Now, she was a distinguished alumnus. She is a distinguished alumnus of IIT Kharagpur, IBM Faculty Award winner for Women in Technology Leadership and VLSI Society of India. So, with this is her type of actually background and experience in research and other field, I'm sure her lecture is going to be a landmark lecture in this series. And I do not know actually if our Vice Chancellor is actually present. Possibly she has not come, and the other directors are also not there. So therefore now I'll request Professor Susmita Surkole to make her actually presentation, and it will be followed by question and answer. Okay. So Professor Kole, please, you can now share your.
Yes. Thank you, Professor Acharya, for inviting me and for the very kind introduction. Let me share my screen. Is it visible?
Yes, perfect.
Okay. So today I'll describe this field. We have been hearing about quantum computers, quantum computing, and my background being in computer science, and I have been working in the area of electronic design automation for almost more than 4 decades now. About 15 years ago, I started exploring with a PhD student of mine how those methods can be applied for quantum computing and how they are different. So today's agenda, I'll try to introduce quantum computing, what it is and how is it different from the kind of computing we are familiar with, and then go into the details of how to go from quantum algorithms to building systems. The two parts are there, the compilation, going from algorithms to the circuit synthesis, and then we need error correction and noise mitigation. I'll tell you why. And of course, a few parting remarks. I have a list of collaborators, mostly my students and collaborators. Amlan Chakraborty was my first student with whom I started this journey in the field of quantum computing. And Ritojit and Devoshmita have just graduated and have been offered jobs in IBM Quantum. So what were the major drivers of quantum computing? On the left, is the mouse visible? Is the cursor visible?
Yes,
when
yes.
I'm moving the cursor, is it visible? Yeah.
Visible,
so
visible.
the one,
Yes.
so the figure that you see on the left is Charles Babbage's electromechanical computer. And then in the middle, we have a wafer, a silicon wafer, and the little squares are the dies which are packaged into the chips. We have at least one in our pockets because all of us are carrying mobile phones and they have chips. And gradually, we are getting to the level where the size of these silicon or nanotechnology devices are getting very small. So what has driven us towards quantum computing? There were two major limitations. We are hitting the wall. One is as the size is diminishing, we have chips with 3 nanometer feature sizes. Just to give an idea, the diameter of human hair is 0.05 millimeter. Red blood cell is 7,000 nanometer. Flu virus is 100 nanometer. So you can imagine feature size means that, a transistor can have about the size of one transistor could be of the order of 10 nanometer. So you can imagine having billions of transistor within, 2.5 centimeter by 2.5 centimeter chip sitting very close by. So what happens is that they are getting smaller and of course faster. They're reaching the limits of classical physics. And therefore, some of the effects, quantum mechanical effects, are to be considered. And that was something which had been bothering the designers of semiconductor or nanotechnology. And the other driver has been that quantum mechanical laws can speed up the computational process by massive parallelism over classical models. So you get speed, and you can also overcome some of the actual hardware limitation. So that is why quantum computers are being, the research in building quantum computers are being pursued. How will this change our lives? I said that it's going to give us massive parallelism. So particularly in optimization and simulation for very complex real life problems, such as in drug design or finance modeling, climate change, and, autonomous vehicle design, astronomy, and even election predictions, all of these requires lots and lots of computing. And with the help of quantum computing, we hope to speed this up. Particularly, this was driven by Richard Feynman, so a snapshot of history. Alan Turing in 1936, he proposed the Turing machine, which gives the model of computing classical computing that we have. In 1981, Richard Feynman had come to MIT, and I was a graduate student there. And I had actually attended that lecture, but I did not understand the implication of what he meant when he said that there's a lot of room at the bottom to be able to tackle simulation problems for quantum chemistry. It was much later, 20 years, more than 20 years later, when people started looking at quantum computing. And why did people start looking at quantum computing? That was because of these two people. David Deutsch, a theoretical physicist, he showed that with quantum computing, you could actually get exponential speed up over classical computing. And I'll briefly describe how you get that. But this was in 1985. It was sort of a concocted problem, or you may say a toy problem, and it was proof of concept, but still it didn't move people that much until 1994, when mathematician Peter Shor showed that factorization of an integer, a large integer, can be done with a quantum computer much, much faster than a classical computer. And why did people sit up? Because RSA, Rivest, Shamir, and Adelman had come up with this public key crypto system. A lot of e-commerce, etc. At that time, I mean, a lot of communication were beginning to use public key crypto system. And it is based on the fact that multiplying two integers is easy, but factorizing, finding the factors of a large integer is not computationally easy in a classical computer. So when Peter Shor showed that with a quantum algorithm, you can do that fast, then people were very much, excited that can we build such systems? If so, then, cryptography has to be redesigned. And it took quite a lot of time for the experimental physicists to actually show that individual quantum systems can be manipulated, measured, and in a span of 10 years later, the important features or special features of quantum mechanics, such as entanglement, etc., could be actually verified experimentally. So what's the difference? In classical, the smallest unit of information is called a bit. We will assume binary systems for now, although there are higher dimensional systems such as ternary, quaternary, and so on. But most of the works are assume binary system. So in classical computing, digital computing, what we have is a bit can have a value of either 0 or 1 at any instant of time. One of the two values. But in quantum computing, what you can have is a superposition of both 0 and 1. And it's a linear superposition. And the scaling factors A and B are such that they satisfy this condition over here. And they need not be just integers. Of course, they can't be integers because they have to satisfy this. Moreover, they are not only rational numbers, but not only real numbers, but they can be complex numbers as well. And they can be very well represented by a unit sphere, which is called the Bloch sphere, BLOCH. So the entire surface of this unit sphere represents possible states of this computing system, a single unit of quantum computing system. So you can imagine that in classical, we just have two possible states. In quantum, we have infinitely many possible states, uncountably infinite. Okay, but then that's very challenging. How do I manage it? The good thing is that even though this is infinite, any state, any state represented by a vector to the surface of the sphere can be represented in terms of these two, the 0 and the 1, which are known, it's called 0 ket. This is the ket notation. So these are what are known as the basis vectors of this entire vector space of possible quantum states. So what we get is in classical, we don't have any superposition of states, whereas in quantum we have. And because of that, as you increase the number of bits, computational power increase is linearly proportional to the number of bits in classical, whereas here it's exponential in the number of qubits. There itself, you have an advantage. In classical, there is no entanglement. I will describe what it is a few slides later. Whereas in quantum, you have entanglement, which is very specific to quantum systems. Another important feature is classical computation is irreversible. What do I mean by irreversible? That means that by looking at the output, can I say what the input was, which means time can go backwards and forwards. In classical computation, in most cases, that's not possible. Whereas in quantum computation, that is possible. And why is this important? It was shown by Landau in the 1960s that if computation is reversible, then the amount of heat dissipation during the computation is negligible. So given that in today's semiconductor chips, you have billions of transistors sitting very close by, switching at very high frequency, a lot of heat is generated. Switching, that means change of state is where you dissipate energy, okay? And so that's why it leads to heating up of the chips. You need to cool the data centers where a lot of computing is happening and a lot of switching is happening. But if you were able to do quantum computing in in room temperature, you would be able to get rid of all that heating up. But there are some flip sides to it. There are some challenges. In classical bit, you can copy. That means copy means you can read and then write. And also, therefore, you can have fan outs. That means the output of a digital gate can be fed to more than one successor gates. However, in quantum, excuse me, you cannot copy. There is a famous no cloning theorem. And why is that? Because this quantum system is supposed to be an isolated, in isolation, and it's supposed to be a closed system. Because the moment there is an interaction with the environment, then this superposition can get disturbed. Sorry. And because you can't copy, you can't have fan-out. And classical computing is robust and can at room temperatures. Quantum computing, that's where the challenge comes, is very fragile. It needs ultra cold temperatures, close to millikelvin, very close to absolute zero. And it has very high error rates because, as I said, you need them to be in isolation. If it is long enough time, you don't have perfect vacuum, so therefore there is going to be disturbance and there are going to be errors. So the bottom line is for mundane tasks, for computations for which classical computers are fast, we'll continue with them. But it's only for complex simulation and for certain problems for which quantum computers, quantum algorithms give exponential speed up, we are going to use quantum computers. Reversible computation, I already talked about that. Let me just elaborate on it just a little bit more. So for example, the famous OR gate, okay? We have Boolean inputs over here, okay? A and B, two inputs and one output. So depending on the combination, if both are zero, the output is zero. But if one of the two is one, then the output is one. Why is it irreversible? Because if the output is one, you cannot say which of these three were the inputs. That's why it's irreversible. So the OR gate is irreversible. The NOT gate, which is one input and one output, if the input is zero, the output is one, and if the input is one, the output is zero, that is reversible. But any multi-input classical gate with a single output is irreversible. But the good news is that you can convert an irreversible function to a reversible one by adding certain output, extra output bits and certain constant inputs. So these are called garbage outputs and the constant inputs are called ancilla. And let's look at it, see how we can do that. So what happens is that so what we have over here is the NOT gate was reversible. Now we can make what is known as a C NOT gate as a 2-qubit. Why are we adding these? Because one of the conditions for reversibility is that it's a one-to-one function. It's the combinations of the input possible input vectors that you have, the bit combinations. They have one-to-one relation with the bit combinations that you have in the output. So it's basically a permutation of these with this. Then only you can uniquely. So the input and the output vectors have to be of the same bit width, same number of bits in the input and output. But the actual function does not need same number of bits. So the other outputs are what are known as garbage outputs. So some reversible gates, which we will talk about, is a control NOT gate. We have 2 qubits. These are the 2 inputs. And the top one, X1, is called the control. And the lower one, X2, is called the target. So only when the control is 1, if the control is 0, nothing happens to the target. I mean, the output of the of this gate is same as what was the input. So both the inputs and the outputs are the same. Only when the control is 1 does the output flip. The NOT operation happens only when the control bit, qubit or control bit is 1. So that's why it's called a control NOT gate. You can extend this. You can make it having 2 control signals and 1 target signals. If only when, and now this is known as a Toffoli gate proposed by the mathematician Tommaso Toffoli. And the implication of this is it is a universal gate in the sense that with the same gate, by setting the control units, control bits correct in a proper manner, you can have different operations. So if you set both the inputs to be control bits to be 1, you will have the NOT operation on the target. Okay, so that's how you get the NOT gate. Now, if you set the values in this manner, that is the target input is 0, and irrespective of what you have in the control unit, the output of the target line is going to be the AND of these two. Okay, so that's how you get both NOT and AND. And once you get NOT and AND, you can realize any 2 input functions, any 2 input Boolean functions with this gate. So that's why it's called a universal gate. So far we've been seeing zeros and ones. We haven't seen anything complex. So now let's get to what are known as quantum gates. And the way these gates are represented, the functioning of these operations or gates are represented are in the form of a matrix. So if you have 1 input, you can have 2 possible basis states, that is a 0 gate and a 1 gate, and similarly 2 possible basis states for the output state. So that's why you have a 2 cross 2 matrix to represent a 1 input gate. If you have n qubits, then you will have 2 to the n possible possible basis states, and that's why you will have 2 to the n cross 2 to the n matrix to represent this in pattern. So remember the block sphere? It was a 3D sphere. So Rx theta is actually the rotation of the state vector, or any vector, unit vector on the surface of this unit sphere. It is rotated about the x-axis by an angle theta. Then this is the equivalent operation that will be done on whatever state you have. Similarly about the y-axis, similarly about the z-axis. So actually the NOT operation that we saw is equivalent to having a rotation about the x-axis by 180 degree and multiplied by the imaginary number. Similarly, we have Y gates and Z gates and some other special gates. I would bring attention to this special gate, which is called the Hadamard gate. And is what the Hadamard gate does is, if it is operated, so how operating it means you multiply the matrix with the state vector. The state vector will be, if it's a 1 qubit, so if we have the state phi as a times 0 ket plus b times 1 ket. So the vector that we will have here is a and b. And so suppose I multiply the Hadamard gate on the 0 ket. So 0 ket is represented by 1 and 0. A is 1 and b is 0. So if you multiply this matrix with 1, 0, what you will get is both 0 ket and 1 ket divided by 1 by root. That means that is equal superposition of both the basis states. And those squares of A and B, the complex numbers, they actually represent, that's why we wanted them to be adding up to 1. They actually represent the probability with which, when you measure, that means measurement means it's interacting with the environment. What is the probability that the state will collapse to the zero ket, that is modulus of A whole square? And what is the probability that it'll collapse to the 1 ket state, that is modulus of B whole square? That's why they have to add up to 1, because those are the two possible states. It will always, after when you measure, you will always get the basis states. And there are two possible basis states, so the two possible probabilities have to add up to 1. And I've written something called FT gate. FT stands for fault tolerance. We will talk about that very soon. So what is a quantum circuit? A quantum circuit is a cascade of quantum gates applied to qubits. And so here, so for example, this was the control NOT or the C NOT gate. Here we have the X, which is the NOT gate. Here we have the Z gate. And this represents a swap gate, which means the whatever states the input qubits were, after it passes through the swap gate, the states are changed, I mean exchanged over here. So I have three stages of operations. And although it is represented like this, as we do in classical digital circuit, the output of, you have input lines coming in, wires coming into a gate, and the output wires connecting to another gate, and then again, the output of this going to another gate, and so on. In quantum, there are no wires. This is just a schematic of representing the sequence of operations. So this is actually representing time, and this is representing space. If you look into a chip, an IC, integrated circuit chip, through a microscope, you will be able to see these operational gates, the NAND gates, the NOT gates, and even more resolution can show you the transistors forming these gates. You would be able to see the wires connecting those. If you look at a quantum computer, you will not find any wires, you will not find any gates. What you will find are just the qubits, the closed computing systems, each unit of computing systems. So you may ask, where do we get the gates? Okay, the gates are nothing but electromagnetic pulses applied on these closed quantum computing units, which causes them to change states. Just as, so depending on what kind of operation you want, you would have to apply pulses on the corresponding qubits in that manner. So a lot of this control control design is also a big challenge in getting quantum circuits to operate correctly. Now, when you're doing a design, be it a bridge, a road, or a building, or a circuit, you have certain metrics, and the design needs to optimize certain metrics. So the corresponding matrix, when you design a chip in traditional IC technology, you want to minimize the area, you want to minimize the power, you want to minimize the delay from the input to the output, so that you can operate in a very fast, at a very high frequency in the gigahertz range. In the case of quantum computing, what are the metrics? You want to minimize the number of qubits because that's very expensive. You also want to minimize the number of quantum gates. Again, electromagnetic pulses have to be operated. And also the number of cycles, I mean, the time-wise. Why? Because there's something called the decoherence time for this quantum computing, the basic unit of quantum computing system, beyond which the state is going to change. So you have to do whatever computation you want to do within the decoherence time to get a reliable output. So I have already talked about superposition. Now let me talk about entanglement. So superposition, remember, we do with the help of this Hadamard gate over here. Now, suppose I have a state of 2 or more qubits. So I have a 2-qubit system. This qubit is initialized to 0 ket, and the next one to 0 ket as well. So on the first qubit, I perform the Hadamard operation in the first time cycle. So this is the qubit 0. I perform the Hadamard operation. Hadamard is represented by, and this is what you will get if you operate it on the 0 ket. You'll get 1 by root 2 0 ket plus 1 ket. Okay, so the A's and the B's are 1 by root 2, and therefore the squares of them are half. So that means there's equal superposition. If you measure, there's equal probability that it might collapse to either 0 or 1. And this symbol over here, the red cross that you see, the encircled cross, that is known as a tensor product. When you have these two operations, these are independent systems. So in parallel, they are operating. So the second qubit remains 0 in the first cycle. So the psi1 that you get here is this. Okay, this is a short form of a 0 ket. 0 ket tensor 0 ket is written as 0, 0. 1 ket tensor 0 is written as 1, 0. Then you perform the C0 operation. So this has both 0 and 1, equal superposition. So what happens is over here that because this one is 0, this doesn't change. So it remains 0, 0. But because this one is 1, this 0 flips to 1, and this is the state that I get, 1, 1. So at the output of this circuit over here, a Hadamard followed by a C0, the state that I get is 1 by root 2 of 0, 0 ket plus 1 by root 2 of 1, 1 ket. If you cannot represent a state as a tensor product of 2 qubits, then we say that it's an entangled state. That means they are not independent. By somehow, if you have the information of one of the qubits, you will be able to infer what the other qubit is if you have entangled them in a certain way. And this is very useful in quantum communication. So what is the power of quantum? I'm going pretty slow. I'll speed up a bit. Power of quantum computing in terms of algorithms, the Deutsch's oracle problem, the factorization problem. So if you want to factor 50-digit integer in classical computer, you may be able to do it in 1 second. In quantum, it may need quite a bit of time because you have to reset and you have to feed and all that. Okay, you have to encode, initialize. Now, if you go on increasing to 100 digits, it's about the same. And the moment you go to 200 digits, you begin to see the importance of quantum computing. And 2000 digits, no way classical computing. You have to do quantum computing. Another important development way back in the mid-90s for quantum computing algorithms was database search. So if you have a list of items having n entries which are not sorted, if it is sorted, you can apply binary search to in order log n time, you can find out whether a given entry exists in the list or not. But if it is not sorted, you would have, in the worst case, have to look at all the n entries. So it would take order n comparisons. But with quantum computing, you can do order square root of n comparisons. So while factorization and Deutsch's problem gives exponential speed up, Grover's algorithm for database search gives you polynomial speed up. For quantum chemistry, there is exponential speed up. There's a website called Quantum Algorithms Zoo, which keeps track of all the quantum algorithms having been developed so far. And those of you who are interested, they also give the details of how much speed up you have of the quantum algorithm over the classical algorithm. So very quickly, what does the Deutsch-Joshua problem do? You have a function of n bit strings as input and 1 bit as output. So this is an irreversible function. Now you are told that the function is either constant, that means for all possible values of the n-bit inputs, the output is the same, either 0 for all of them or 1 for all of them. Okay, so that's a constant function. Or it's a balanced function. That means for n-bit input, you can have 2 to the n possible input combinations. So for half of the 2 to the n, that's 2 to the n minus 1, the values, you don't know which half, the value is 0, and for the other half, the value is 1. So that's called a balanced function. Okay. So you're promised, this is a black box function. You don't know what the function is, but you're just told that it's either constant or balanced. And the question that you're asked is, tell me whether this is constant or balanced. Okay. Now, for classical computing, what you have to do is, in a very naive way, you will feed all the 2 to the n combinations, check whether all of them are the same, or half of them are 0 and half of them are 1. So order 2 to the n. To be very precise, you can do with 2 to the n minus 1 plus 1. That means if the extra 1 gives same, then you know it's constant. You don't need to proceed. Okay? But if it's different, then you know it's balanced. So in Deutsch-Tauscher algorithm, what you do is you have n qubits because there are n inputs in the binary function, in the function that you have. You perform Hadamard operation all on the n qubits. This is a single qubit operation. But in parallel, what you will get is a superposition of all these n qubits, and you get the 2 to the n possible superposition with equal probability. And you have an extra qubit over here. Also, you do this. And then you have what is known as a quantum function, which is related to the black box function. You apply that quantum function, and then again you do Hadamard and you measure. If the function was constant, what you measure will be all zeros. And if it is balanced, then this will never be zero. So with just one operation of the function, this is where massive parallelism is occurring. With one quantum query, you can answer the question. So therefore, classical query complexity was this much, and quantum query complexity is this much. You could do random, but there is a probability of failure. Okay? So this actually separates the class of problems which can be solved deterministically, classically in polynomial time, and the exact quantum polynomial time. So this is a problem which can be solved in exact polynomial time, but not in classical polynomial time. The next one is more fascinating, the Shor's algorithm, and that's the main driver. So this sequence of digits is actually one integer, a large integer, which is the product of these two large integers. And in the best classical algorithm, to get this would need this much time, where n is the number of digits. So if it's a 300 digit, this is the amount of time. Shor's algorithm can solve it in polynomial time. Okay, the idea is, I'm not going to go through the details of the algorithm, but the idea is fascinating. It's very, very simple. It makes use of a very old result from number theory. So this is the number that I want to factor. I choose another number less than that, and which does not have any common factors with this number. Now, if I keep raising this number to powers and take the modulo of 21. What is modulo of 21? You divide by 21 and whatever is the remainder. So 2 to the 4 is 16. 16 modulo 21 is of course 16, but 2 to the 5 is 32. 32 modulo 21 is 11. That's the remainder. And if you raise it to 6 power, you get modulo as 1, remainder is 1. So 2 to the 0 is 1. So 2 to the 0 modulo 21 was 1. 2 to the 6 modulo 21 is 1 again. This the number theoretic result says that this function is periodic, and the value of r for which it becomes 1 again, the periodicity is an integer. So let's call y to be equal to 2 to the r by 2 modulo 1. So if r was 6, we have 8. Now look at 8 minus 1 and 8 plus 1 and take the GCD of those with the number that I wanted to factorize. And lo and behold, I get the factors of n. This is not magic. This is very simple. Because you see what y was defined as this. So if I take y square, that is actually x to the power r. Y was x to the power r by 2 modulo n. So y square is x to the power r modulo n equal to 1. So if I deduct 1 from this, y square minus 1, it should be, the remainder should be 0, and it should be exactly divisible by n. So which means because y is less than n minus 1, y minus 1 and y plus 1 are at most n minus 1. So therefore, these two, at least one of them should share a factor, because this is exactly divisible by n, so should share a factor. And that's what we are doing over here, the non-trivial factors. This we learned, this is something we, this kind of thing we learned in middle school. So why couldn't we do it in classical for all these years? Well, finding the period r in classical is exponential time, whereas Shor gave a quantum algorithm which found r in polynomial time. Okay, so that's why we have quantum algorithms in real life. Now, those are algorithms. So to build quantum algorithms, let's get to quantum compilation. You need computer scientists, both mathematicians, theoretical computer scientists to do the algorithm design. You need both theoretical physicists and experimental physicists to build the system. And you also need people like us to come up with, fast and optimal methods to map this algorithm onto the hardware. And what are the optimization problems? Okay, the criteria we want them to be scalable so that, whatever method you have, you can easily expand it. And you should be able to initialize that in a simple state, like all zeros. We want reliable gate operations so that the qubits are sufficiently isolated, and the technology is such that there's long decoherence time, and the measurements should be reliable. Additional challenges, no cloning. So how do we test? How do we detect and correct errors? And the control is classical. So it has to be very precise. Otherwise, control errors are going to affect the operation errors. Here's a report of 2023 of how quantum computing has progressed in the past 5 years. Okay, scale up is happening, quantum control is happening, quantum error correction is way beyond. We need to improve algorithms in order to be able to apply to science and society. The number of gates has to increase, and the number of qubits also has to increase. We still don't have more. The latest IBM is some 1,000 plus qubits. They are trying to get to 4,000 plus qubits. It's only end of this year they may be able to. Right now, IBM has made it available over cloud, over internet. Users can only use up to 127 or 133 qubits. The others are still not that reliable to be open to public. What do you mean that reliable? The error rates of the qubits is high. Now, how do I map this circuit? So I have a quantum algorithm. There are some classical functions. There are some quantum functions. I have to convert the classical functions to reversible logic. Quantum functions by them are reversible. So you can make use of some already existing methods. They are not optimal, they are efficient, polynomial time. You can use some library of the typical quantum functions. You have a finite number of them. So what you get is you combine them to get quantum logic, but that doesn't ensure fault tolerance. And this part did not consider what technology you are using. Now bring in the technology mapping. So depending on the particular technology, you will have certain gate library. And then not all the gates are going to be fault tolerant. So you have to again transform them to fault tolerant gates, and then you get the fault tolerant quantum logic. This is still at the logic level. Then you have to actually map them onto physical qubits. And to make them reliable, you would need error correction, and you would have to do again some more optimization over there. So I was involved in these two systems that we published, particularly the physical design, where because my bread and butter for since I started research was physical design for electronic systems, and then also for quantum systems. And this is where you would get. Now, I talked about technology mapping. So currently, you have more or less 6 technologies here: quantum dots, superconducting, ion trap, neutral atom, linear photons, and nonlinear photons. And depending on the technology, you have these primitive gates, quantum gates, which can be implemented right away. Okay. So notice that we talked of C naught. Okay. We talked of Hadamard. But in all the technologies, we don't have Hadamard, we don't have C naught. So then what do? Well, we do have what are known as logic identities. So in a technology where we don't have a Hadamard, we do have some identities. So the Hadamard operation can be expressed in terms of 3 rotation, first about Z, then about X, and then about Z again, to get, the Hadamard operation. Therefore, they have several different decomposition. It depends on the structure, and that will also give the minimization of the number of operations, gate operations, and so for example, the C naught, it was there only in the photonics. For the other ones, it was not there. So you would need about, in some of the technologies, you need 3 primitive operations. In some others, you need 5 primitive operations. So therefore, the number of operations, the cost would depend on the technology, and the kind of gate that you have would, again, depending on the number of primitive operations, whether the operation you're looking at, whether it's primitive or not, the cost is going to differ, and the number of time cycles is also going to differ. So all this have to be taken into account in the synthesis that you have. So in this fault-tolerant quantum logic synthesis method, okay, first, in the behavioral domain, that is independent of the technology, some amount of optimization of the number of operations was done. Then, taking into account the specific technology that's going to be used, and therefore the gate library, some more optimization was done. And finally, to use the fault-tolerant gates only, some more optimization was done. Okay, and to just show a result, 3 optimizations without fault tolerance. You can see that this was for a particular circuit, which is the 4-bit quantum Fourier transform, which is very much related to the Shor's algorithm of factorization. With the first level and the second level of optimization, you get some amount of reduction in the number of operations, in the number of cycles, depending on the kind of technology that you're doing. And after you do the fault tolerance, you get a further reduction. Okay, so there is quite a bit of improvement. And for the 8-qubit, you get more improvement. And so 3-stage optimization is better. And the time required is not too much. It was very efficient in that sense. Now I talked about physical mapping. So let me quickly tell you why this is important. So we have these qubits. Now we want to place them on a grid of available qubits which have been manufactured. And suppose I have to do a C0 operation between S0, a qubit in S0 and a qubit in S8. It is better to bring them next to each other. Because remember, we are going to apply electromagnetic pulses. If they are not nearest neighbors, then the operation is going to be defective. So in order to bring them, we will have to do some swap operations. So first I swap S5 with S8, then I swap S5 and S2, and then I have S8 and S1 next to each other. So I wanted to do a C0 between S1 and S8. So that means these are extra operations. So how I place the qubits in the circuit on the actual fabric is going to determine the number of extra swap operations. So let me show you this. So this is a circuit that we got. These are C0 operations. I have 6 qubits, and I place Q0 onto S0, the first. So this is the grid in which that I'm going to map these or assign these qubits. So this is the first C0 operation between S0 and S5, which are far apart. So I need 2 swap operations to bring them next to each other. And then, so as I go along, I'll need some more swap operations. And the cost, if it's trivial mapping, then the cost number of extra swaps is 6. But if I had mapped Q0 to S0 and Q5 to S5, Q4 to S4, Q1 to S1, and I have actually ordered them in this manner instead of this manner. S0, S1, S2, S3, S4, S5. Instead of that, I have S0, S5, S4, S1, S3, S2. Then a single swap is available. So how do I do this mapping? And that is what we had done. We had shown that you can do this with a greedy algorithm. It's an NP computing problem. You can do it in the size of the grid and the number of qubits. It's polynomial time. And after, what is routing? Routing was how you build the swap chains. So I could have gone this way, I could have gone this way, I could have gone midway. So there are a number of ways, okay? And that's dynamic because after you make one operation, then it's a different pair which need to be. So again, this was pretty efficient, okay? Now, I talked about quantum error correction. Why do I need this? So this is a cartoon which says that, quantum supremacy can claim that whatever you do, I can do better. But the reality is that you need to fix errors, which is the fault tolerant error. And actually what we have now is noisy intermediate scale quantum error, okay? Because we don't have enough of them. So first, quickly, let me talk about quantum error correction, okay? And why do we need it? Okay, as I said, that classical qubit and quantum qubit. Now, what does this read? Does it read true or does it read false? Okay, so it could read both. So suppose I have a 2-qubit entangled state like this, and the corresponding circuit needed to do this entanglement is over here. Just to remind you, these are the gate operations, the H gate, the X gate, and so on. Okay, so if you run on a simulator, which is having those matrices, you would get that the 0-1 ket and the 1-0 ket, these are the two possible states which are entangled with equal superposition. So there's a probability half you will get 0-1, with another probability very close to half you will get 1-0. But if you run on an actual quantum machine, there is more than non-zero probability of getting 0, 0, and 1, 1, which is erroneous. Okay, it's the right answers are having high probability, but the wrong answers also have non-zero probability. So that's why we need to do error correction. Okay. So encoding we've done in classical, and in classical we just have bit flip. Here we also have phase flip because the unit vector can have a certain angle in the unit sphere. So if a quantum error correcting code can correct both X, Y, and Z error, then it can correct any kind of error. Single error detecting and correcting codes were proposed, making sure Steen and Neil code. So what happens is one logical qubit is encoded in 9 physical qubits for Bacon-Shor code. So to do a QECC-aware synthesis for a given error probability of a primitive gate in a particular technology, physical machine description, you compute the error probability at the QECC tile level. That means these are, spread out in a 2D array, arranged in a 2D array. What is the error probability and where would you like to insert the QECC? If you do 2D nearest neighbor placement, also, as we saw in PAQCS, we found that you need to keep into account what kind of code you're using. Depending on that, the array of qubits will be of that sort, and you will have to do the placement in that manner. I think I'm running out of time, so I will skip this part. The idea of repetitive code is there in quantum error correction, but you can't copy. So that's why what you have to do is use additional qubits. You can't measure, you can't copy. In order to detect an error, you have to measure and check which of the bits are erroneous. Because you can't do that, you use these extra qubits, which kind of affect whether if there's an error here, it will affect the ancilla qubit, and depending on the measurement here, you would be able to decode on which of these qubits there was an error. So I'll skip this. Okay. Now, once you get the error, this thing that you measure is called the error syndrome. Looking at the syndrome, you would be able to decode which bit is erroneous, and then you will apply the inverse operation to correct the error. Now, so error syndrome decoding is an important operation, and the problem is that syndromes do not map to error configurations one-to-one. That means that more than one errors can map to the same syndrome. Therefore, error syndrome decoding is also a hard problem. Classically, some deterministic polynomial time algorithms were used without taking into consideration probability of error. But what happened was it could, in certain cases, introduce more errors. Some researchers proposed machine learning-based decoders, which outperformed the traditional decoders. We also proposed a more advanced level machine learning based decoder, and it got higher values of what are known as threshold and pseudo threshold. Pseudo threshold is the logical error probability rate below which the physical error probability is lower, so you need to operate in that zone. And the threshold is beyond which encoding doesn't work anymore. The quantum error correction doesn't work anymore. You see, the level of encoding gives you the distance of encoding. So beyond the threshold, so the higher the values of error probability, that means you can operate smoothly for a longer time. We can also reduce error by what is known as circuit cutting. We did some work in this area also. That was my alarm. Uh, so we did some machine learning based error prediction. What we have seen is for larger circuits, the error rate is higher. So what you can do is have smaller circuits, that is circuit cutting, and fragment them in a way, in an intelligent way, so that it's influenced by the amount of error prediction for these subcircuits. And you run it on quantum hardware, which is a smaller number of qubits than the original quantum circuit has, get the final outcome, and then classically you combine them. This will, of course, take quite a bit of time. So you have to do it very carefully. And this has resulted in quite a bit of reduction in error in operation. How you now you can use machine learning, you can use even a quantum algorithm to do the bipartitioning and look at which is doing better, and we found that you could actually beat this. So this is all I will talk about error correction. For the noisy intermediate scale, with the noisy qubits, you don't have the luxury of error correction. You have at most a few hundred qubits. So we need algorithms which will use small number of qubits, uh, less depth, and also noise-aware scheduling on hardware. Okay, so what's so for the NISQ era, what we have is a hybrid quantum classical algorithm. We have some classical optimizer, and only some portion of the they feed some parameters for the quantum circuit, and we perform the quantum operations on it, measure the output, and check whether it's good enough. Otherwise, we revise the parameters, and so this can be used for quantum combinatorial optimization, and we come up with what are known as quantum approximate optimization algorithm. So this is a graph theoretic problem. And given a graph, I want to find the maximum number of edges, which when removed will give me two components, so that I get a bipartite graph. And with the help of this, a classically hard problem, exponential time, but with the quantum circuit, you again, you don't get exact solution, but you get a close enough solution. And the circuitry is something like this. For each edge, you have a small circuit like this, and you also have this. And you have to iterate between these will mean parameters beta and gamma, as these are supplied by the classical one over there. Now, the problem is that in this hardware, the error probability of 2-qubit gates is 100 times more than 1 qubit. So the goal is to optimize the circuit in such a way that I reduce the number of 2-qubit circuits. So we applied some graph algorithm approaches to reduce the 2-qubit gates. There are some conditions on which I can remove the first C0 gate, and so because these are equivalent, and this of course works if there is equal superposition. So we applied the depth first search graph theoretic algorithm to eliminate. So this was the original circuit for the max cut for this graph. For each edge, I have 7 edges. For each edge, I have this sort of pairs of circuits. And if I do a depth first ordering of the nodes, then for the first encounter of these vertices, I can remove the first C0. So since depth first search traversal of a graph of n vertices, even if it has order n squared, n into n minus 1 by 2 edges, it will have what are known as n minus 1 tree edges. And for all those tree edges, you can remove the C0. So you can remove optimal number of. But the depth of the circuit has increased. Okay, that means what is the depth? The number of levels. You can't do parallel operation of this because both of these are involved with the same qubit. Okay, for one it is the target qubit, for the other is the control qubit. So similarly like that. So therefore, we saw that it's related to the height of the spanning tree. If you have a tree like this, the depth is 14. If you have a different tree like this, then the depth is less. But that's not enough. Just reducing the spanning tree. Even though they have the same height, the depth is the same. So we proposed a greedy algorithm which takes into account the branching, and with that we could actually, this is without the traditional one, without any representation, without any elimination of the first C naught. This is with the straightaway first C naught, and this is with our greedy algorithm. So what is this? This is the probability of error. Okay, so the probability of error has gone down much less as the number of vertices increases. We measure with what is called the fidelity of the ideal state and the noisy state. Higher the overlap, better the outcome. Okay, so and the depth actually of the spanning tree is the maximum height of the original one. And if we have different branching factors forced into it, we get better and better. Okay, now that didn't take into account the hardware. Okay, so the swap reduction in the swap, depending on the topology, again, we can improve, and we got. As far as the swaps are concerned, again, how you map uh, in, earlier in the PAQCS, we took that all qubits and all operations have this, either all qubits have the same error rates and all 2-qubit operations have the same error rates. But that's not the case. So if you want to take that into account, again, we did noise-aware job scheduling with an ILP formulation, and we got quite a bit of reduction in error rate. If the number of hardware available and the number of circuits is more than the number of circuits, we can have exact solution. If it is less, then we have to do it in batches. Okay, and so that's more or less describing in a nutshell what are the optimization of various things that are required to map a circuit onto a quantum system. We have the National Quantum Mission with quantum computing, communication, sensing and metrology, and materials and devices. Hope a lot more effort will go in. For parting remarks, what are the things we need to keep in mind? There are still synthesis issues, that is logic level optimization and better error prediction, physical mapping for now. The experimental physicists are coming up with 3D grid of qubits instead of planar 2D grid. And what does that mean? The noise models that the earlier QECCs have are more simplistic. Realistic models have far more complicated noise. So we need more realistic error models and corresponding QECCs to come up with more efficient circuits and corresponding syndrome decoding, quantum controller verification, testing. Also, there are some researchers who are working with security and IP protection. So much optimization efforts are being put in to come up with, reduce the cost to get a circuit. I need to, there are companies which are doing this. I need to protect the designs that we come up with. And a big question, these are the two big computing paradigms, quantum computing and AI. And what is the relation? I have not covered that much. You have machine learning, you have quantum computing. Now, you see, people talk of quantum machine learning, but it's not that it's not that simple, because all the challenges of quantum circuits will remain. Uh, Machine learning is good for classification and those kinds of problems. Quantum is better for optimization. So we may use quantum machine learning in some of the complicated cases, but we are still not there yet. We need more quantum algorithms for real life applications. So the way it is being put that the future of computing is quantum processor aided supercomputing. You may have a supercomputer which may be using AI algorithms, but some of the jobs, some of the tasks for which we have exponential speed ups with quantum algorithms, we can offload it to a quantum processor, get the output, and then continue with computing. I'm sorry I ran over time, and I would be happy to take questions. Thank you very much for your attention.
Thank you so much for your excellent talk. Now, we'd like to have a few more questions from our participants.
Good evening, ma'am. Hello.
Yes.
Hello.
Hello.
Yeah, good evening, ma'am. Very nice, very nice lecture, ma'am. Thank you. So basically, I am from mechanical engineering. So these are the new terminologies. Actually, I learned since this session. What about the present status of quantum computing technology in India, and what about its forecasting? I mean, the prediction of the future about the quantum computing, either globally or in context in India.
Okay. I did share a slide which is slightly old, maybe. No, sorry. I probably went through it a little too fast.
Okay.
Okay. So this is with respect to this is something IBM's roadmap. Google has recently announced that it has come up with what was it about 123. So all the computing that I have described are for discrete quantum computing. You have a different kind of quantum computing which is based on quantum annealing, and there's a company called D-Wave which claims that it has that's more of adiabatic computing and more continuous domain. So it handles many more qubits. It says that it has more qubits, but those type of quantum computers are not for all kinds of computing. So currently, IBM has 1,000 plus qubits, and by the end of this year, it is hoping to have 4,000 plus qubits. By 2030, if they get to around 10,000 qubits, we would be able to do
Computation.
yeah, we would be. So as you can see over here, to do some meaningful applications, 10 to the 5 qubits, there you would be able to also have some amount of quantum error correction, and we can apply gates. And we also need to improve the error rates, because trying to have operations of 10 to the 12 gates within the decoherence time of a few nanoseconds is going to be a big challenge. Among the different technologies, I don't have it here. What I can say is quantum dot has a very long decoherence time of the order of milliseconds, but the flip side is its error rate is also high. Ion trap is best in terms of error rates, very low error rates, but the decoherence time is also slow. So a lot of work needs to be done by the experimental physicist. As far as India is concerned, the IFR has produced a 5-qubit circuit. It's getting to some more, but it's very expensive. And as you know, it would need some more time. I hope that answers my question.
Yes, ma'am. Yes, ma'am. Thank you so much. Thank you.
There is Tripathi here, A.K. Tripathi. I think, madam, you
Yes.
are correct. I am also associated with the Department of Science and Technology. They have a quantum mission. I have read some of the articles there. The highest number of qubit handled by any IIT is only 8, no, 8 or 9. And several proposals have been submitted to DST and money has been allocated. And they are all fighting with each other to show that they are better than the other. But considering that your graph shows 10 to the power 2, 10 to the power 3 number of qubits to give really challenging issues that is facing today for quantum computing, how far India is behind and is it worth, I mean, I'm just asking 500 crores is the quantum mission India is spending. I mean, as we go ahead, some companies will be declaring that they have the hardware and all that. Should we make our application so complicated that we need the most sophisticated computer to solve it, or we should limit our ambition to something which is manageable?
So that's why we have these other themes, which is quantum communication, which would be and quantum sensors. Okay, those are more. They don't need too many qubits for as quantum computing does. Okay, so there are researchers, there are research groups which are working in those, and they seem to be, I would say, more promising to me than you know building quantum computers. But there are very few people who are working in the kind of type of research problems that my group and just a handful. I mean, very few people are working with design automation, and this is something computer scientists can do, even though we don't build. I mean, that's what we've been doing with IC technology. It's only recently that this India semiconductor mission has been announced, and we are going to, manufacture some chips, but they are not cutting edge like Taiwan. They are not 3 nanometer, 7 nanometer. They would be at most, I think, 45 nanometer or so. May aim at 28 nanometer. But that's old technology. But that's good for certain applications. We don't, need too much technology for everything because that's going to make it very expensive. But all these years, since the mid 90s, there have been many, many design houses. Okay, we have not produced chips, but we have actually supplied designs to companies. I have had several collaborations with Intel and IBM where we worked on the optimization algorithms, which would make the chips, better in terms of area, power, and delay, and other things like that. But India Semiconductor Mission is to actually go to the complete end and produce chips. In order to be able to do so, we do need fab labs, and to be able to do that by ourselves is going to be difficult. So that's why they have collaborations with. I see, just as fabricating ICs at the cutting edge is very, very complex and very expensive. Similarly, quantum computing, as you know, is only IBM. Even other companies like Rigetti, INQ, or Google, they are going at a slower pace. IBM is the main leader right now. Okay, they have the funds and they are going in. So I would say it would be good to look at materials to get to room temperature or close to much higher temperature kind of quantum qubits, so that we have more less expensive quantum computing. So those are the niche areas where India has the talent and has the capability of actually uh,
And
contributing to the global.
if we look at the TRL level, where do you think quantum computing today is? Level 1, 2, or
What
whether
kind of problems are they solving?
no, technology readiness level, they call it TRL level, that whether the technology is marketable or not. If it is TRL level 7 and 8, it is marketable. If it is a beginning, then it is in 1 and 2. So where do you think quantum computing research in India is today? How far we are from actually producing something hardware which will sell in the market? Or is there anything?
We do have a long way to go. That's all I can say. I'm not an experimental technologist. I'm more of a, user of quantum computers and trying to design. I mean, this is before you go to the quantum computer. You do a lot of optimization so that the quantum computer you need is not too large. Okay. So that's where I would like to contribute. Okay, I have been contributing. So yes, we still have a long way to go. That's all I can say.
Thank you, madam.
Yes, Professor Misra.
I'm a mechanical engineer using the electrical technology to manufacturing the component that I've started in Jadavpur University with Rana. Rana was my classmate. And actually, think what happens, even with not supercomputers, but not there, but in a digital technology, oscilloscopes, we have seen that we have to identify the effective sparks in the EDM machine. And we have to measure that one, which are effective pulses and which are not effective pulses. Then what you have done, if you put two probes in the input and the output, we get a signal. And then
yes,
what we see,
right.
then
So measurement errors are very important, something which is very important and it has to be taken into account. So in some of the work that we have done, I think the last work, the noise aware scheduling, we
correct.
also took into account whether we are doing any correction for measurement error or not. Depending on that, we report the amount of noise reduction. Okay, so as I said, not only in the quantum algorithm domain and the quantum qubit design domain, but also in the classical peripherals, that means the control, the measurement, lot more attention needs to be put in.
Good. That's the thing. We have to take it sportively. Any research, we have to take sportive. What is the effective use of those things? We
Sorry,
have to continue
I didn't get your question, please.
No, it's not a question. It's just to accept it, what you said. It is acknowledgement. Nothing
Yes.
else.
Thank you.
Any other question? Sanat Kumar ji, would you like to ask some question?
Yes, madam. You kindly put yourself in George Gamow's position. That means I am a total useless fellow on the road, not understanding much. Certainly, this is far above my level. But question that I'm asking you is like this. Can you relate? Somebody was asking about India. Can you relate in India what type of physical problems that we need quantum computer for? For example, you said election results, something you said. I don't know what is the complexities involved. Our elections cannot be predicted. That's what I think. But anyway, so can you list for me some kind of problems which require this quantum? We have lived 10,000 years without quantum computing. Why do we need them now? Thank you.
Okay. So, for example, I had this slide. I think there are. I mean, pharmaceuticals is a big thing and chemical production of various types of chemicals is a big industry in India. In fact, India uh, produces pharmaceuticals, but drug design, uh, not much work is done. It so far, drug design happens in the uh, in situ wet labs, okay, in biochemistry. With the help of simulators, we can speed this up much more. Say 20 years of work in the lab can be cut down to 1 year, okay? So we do have biochemists. Here is one area, and we do have many pharmaceutical companies producing lots of medicines which are supplied to the developing countries. So we have these problem of, generic drugs which are being produced, and also fake drugs. So all that, those area we can focus on. Uh, Another area is, of course, a lot of we are trying to build better infrastructure, better transportation. So, for example, the railways, of late, you will find that most trains run late. And part of it is maybe the tracks are not maintained well, but I think part of it is a scheduling problem. We have introduced so many trains on a particular track. It is almost unrealistically scheduled, and that's the reason why they run late. So we can also use this is a very intricate optimization problem. So these sort of optimization we can do with the help of quantum computing, and have better scheduling so that there are no accidents, and also travel time is less, so the costs are less. These sort of thing comes to my mind right away, where we are manufacturing, and how we can use this. We are using AI, but with the help of quantum computing, we can make it better. Of course, these are going to be possible only when we have reasonably large quantum computers available to us. Otherwise, those will be toy problems.
Okay, I will just ask a parallel question on that. We know that interaction of neutrons with various atoms is rather a random thing, because neutrons are so small and the atom distance between them is so large that you don't know. So it's a random process, which I think today in our calculations we establish requirements by means of experimental values and put some constants and get at the equation. So now, can quantum computing be made to make such random processes more amenable to making up a proper equation, so that we can do the designs further on that? Am I clear?
Yeah, okay. Before I answer it directly, I need to emphasize something, which is that I mentioned that I can have a superposition of states, but the moment I measure, it's going to collapse to one of the basis states with a probability of which is related to the this factor over here, this scale factor over here. Now, the whole purpose of quantum algorithm design is to start from a particular initial state and perform operations so that the probability of a state associated with the correct output, with a correct output, is as high as possible. And the moment I say probability, I incur the fact, or I need to clarify the fact that quantum computing is a probabilistic computing. When you measure, there is a non-zero probability that it might measure a state which is not the correct answer. So that is why you have to repeat the experiment many times. Those are called trials or shots, and take the average over there. So the hope is that with very high probability, you get the correct output. And if you repeat, then the probability that you get the correct output will repeat in the average it will be. So first of all, quantum computing is probabilistic. And then coming to your question of random processes, yes, we have algorithms based on random walk, which is a random process. And we have optimization based on random walk, which can be done more efficiently in quantum computing. Okay, that's all that I know. I don't know whether I've been able to answer your question.
Thank you, madam. This random walk, yes, I am aware of it. Neutron interaction with the moderator is random walk. So
Yes.
they go on trying several trials you do and then try to find out what it is. Okay, I have understood now. Thank you.
Yes, yes.
Madam, should I ask one more questions about the same domain?
Please.
Yeah, here, in case of reversible, is it possible, ma'am? So being a mechanical guys, we know that the irreversible is quite common for this universe, right? In case of reversible, what are the assumptions actually we made? I'm sorry?
Hello? So yes, you have raised a very pertinent point.
Yeah.
Now there are researchers on classical reversible computing where they have actually built CMOS-based systems where reversible computing could be done. Sorry?
Madam, I'm sorry. I never yeah. Hello?
Dr. T. Shekharan, sir, your madam has answered your question. I hope it is fine with you.
Yes, yes,
yes. Okay. Any other questions from the audience, please? So there's no question neither in the chat box.
I have actually a simple thing in my mind. It is true that we cannot really go into producing chipset, say 3 nanometer, 5 nanometer level, etc. Now, but India is definitely going into the production of chips, and in the number of companies are coming, but they may be, as you have told very clearly, they may be of the order of 45 nanometers and all. But there is actually a good demand for VLSI designer.
Yes.
And can we really think of in VLSI design how these quantum computing concepts could be utilized to make it better?
Well, there are a lot of problems which are optimization problems, like the problem that I briefly showed, the max cut problem. That's a very important problem in VLSI physical design. Okay. So there are many graph theoretic, graph algorithm make problem formulations related to VLSI design, physical design, logic optimization, which can now, okay, one word of caution, not all computationally expensive problems in classical can be solved in polynomial time with quantum computing. There are problems. If had that been so, then we would have been in a completely different domain. But that's why we've come up with what are known as quantum approximate algorithms, so that we get fairly good solutions. Classical approximation algorithms, people have been working on that for 3 decades now. And the question is, can we come up with quantum approximation algorithms which beat the classical approximation algorithms, and you get fairly good solutions which can be used for chip design. Yes.
Oh, thank you so much. Now, we have actually with us, one of our partner is the IEEE Bhubaneswar section, and Mr. Tripathi is actually with us. So he should say something about this section. Other partners are not there. So please actually tell something about your section.
Thank you, Dr. Acharya, for giving the opportunity. Actually, IEEE in Bhubaneswar section started as a subsection 15 years back. Roughly, it was 2015, 10 years back. And we continued to be a subsection for about 10 years. And we did quite well. A lot of very national level seminars were conducted in Bhubaneswar that attracted the attention of not only India Council, but also Region 10 in IEEE. And they realized that our continuing to work under Calcutta section as a subsection probably was not justice to the subsection. And we applied, sent a petition for status improvement to the section level, and it has been granted. From November 23, 24 to be exact, we are a full section. We recently celebrated that section opening, and happy to tell that Director Region 10 came, India Council members came, and today we have 11 chapters, societies, and 5 or 6 and 17 student communities and chapters. So we are in big size, and we are recognized all over India today to be a very dynamic section. The calendar is so full for next year that we are asking the institutes to apply for 26 March afterwards, and because the itinerary is fixed for the 25 fully. So I must say that we are complementing the objective of INAE here. We are now in INAE around 30-35 members, and every year the number is increasing. Similarly, in IEEE also, our number is going to increase. Together, I am very hopeful that we will make a sort of a organization which will be known in other part as a leader in technology in all these areas. Why I took interest in the quantum computing is that my colleague in DST is man who is handling quantum computing. He gives me a very optimistic view as well as pessimistic view, in the sense that it will continue to be explored for many years with dependence, heavy dependence on others. So unless we really convert it into something which we can sell and get on revenue from outside, the one directional collaboration and one directional research will satisfy the ambition of institutes in getting PhDs. But then the net result will not be applicable to India unless our application side improves to that extent. So we must also see that where all we can apply so that we get the best result of fast computing. We have done well in supercomputing. I am in track of supercomputing in different fields, and IIT is in Institute of Science where I was a student. We have a nano laboratory also. There are 500 crores nano laboratory working. So all these things tell that this time has come that we should give a big thrust to it, and at least pose challenge to countries, maybe may not be China, Taiwan, or Germany, or USA, but next to them. Next to them, we can be the position in India. We can go to that position. Thank you so much, sir.
Okay. Thank you so much. Before actually we ask our Madam to propose actually vote of thanks, I would just like to inform few things. One thing is, out of 54 distinguished lectures that we had only 5 lady speakers. And Madam, you are one of them. The others are, again, you know all of them practically. Sudeshna Sarkar, Josna Datta Majumdar, Swagata Dasgupta, and one person, that is Janet Allen from University of Oklahoma. We want actually many more lady speakers in this series. So I will request, actually, please help us in finding out few good speakers who can come. And the next thing, the announcement what I have is the 55th distinguished lecture is now scheduled on 25th of this month. And Professor Nitin George of IIT Indore is going to give this lecture. Please join in large numbers. Now, Madam, please propose a vote of thanks. One more thing before vote of thanks I would like to say. So normally we record all these lectures. Your thing is also recorded. But we cannot really circulate unless you permit us to circulate. Do you have any objection?
No, I think that's fine with me.
Okay.
Thank
Thank you so much.
Thank you.
Okay. Now, Madam, please.
Yes, sir. Thank you. Respected dignitaries, esteemed speaker, and dear participants. On behalf of INAE Bhubaneswar chapter, Shiksha Anusandhan deemed to be University Bhubaneswar, CSIR MMT Bhubaneswar, IIT Bhubaneswar, NISER Bhubaneswar, and IEEE Bhubaneswar section, I extend my heartfelt gratitude to Professor Sushmita Sorkole for her enlightening lecture on design automation for quantum computing systems. Madam, your presentation was phenomenal. Such a lucid presentation makes us understand how designing automation for quantum computing system can be done. Thanks to our organizers, the coordinators, faculties, and team members for seamless execution. And special thanks to our engaged elite audience for making this session interactive and very much insightful. We look forward for your participation in future lectures too. Thank you once again to our speaker. Thank you, ma'am. Thank you all. Namaste.
Madam, one more thing, a small memento from our side will be posted to you. We can't give anything, but at least some memento we can really give.
Thank you so
Thank
much.
You so much.
It's an honor for me. Thank you.
Thank you so much.
Thank you so much.
Thank you.
Namaste. Good night.
Bye-bye.